The surfaces of terrestrial bodies have a wide range of characteristics. Earth has a very geologically active surface indicative of heat traveling outward from the core. Other bodies, like the Moon, have dead surfaces with no geologic activity suggesting that there is no heat still escaping. This video will explore the underlying science behind geologic activity and escaping heat. Planets form as a natural byproduct of star formation. 4.6 billion years ago, our solar system was a swirling disk of material surrounding the protosun, which gave rise to planets. In this disk, gases condensed to form solids as temperatures fell. Then solid grains stuck together in a process known as accretion, gradually building up in size. This graphic illustrates the later stages of accretion, where larger chunks of material known as planetesimals are collecting to form a planet. When a planetesimal nears a protoplanet, it is accelerated and pulled in by the planet's gravity. When it collides with the surface, the energy of its motion, kinetic energy, is converted into heat, thermal energy, raising the planet's temperature. In general, planets were hot objects when they were first formed. The greater the size of the planet, the greater the number of planetesimals it takes to make it, and the more thermal energy stored during formation. Thus, the heat energy from accretion is proportional to the volume of the spherical object, given by volume equals 4/3 pi r cubed. Note that heat energy also comes from differentiation, the settling of higher density materials, giving rise to a more compact object. Heat also comes from the decays of radioactive material, think uranium, over billions of years, which turns out to be the largest of the 3 heat generation mechanisms. All 3 heating processes, accretion, differentiation, and radioactive decay, increase with the volume of the body. The loss of heat over time is due to radiation and happens at the surface. Thus, it depends on the surface area of the body. The surface area of a sphere is equal to 4 pi r squared, so the loss of heat over time also increases with size. If we take the ratio of these two effects, heat loss, which is related to surface area, divided by the heat the object has, which is related to volume, we get a measure of the rate at which a planet loses its internal heat. So this measure of rate of heat loss is inversely proportional to radius. A large planet will lose its heat at a slower pace. Even though it loses a lot of heat through its larger surface, it has so much more heat to start with because of its volume. To explore this phenomenon, we have created solid spheres of aluminum of different sizes, a 4-inch diameter, a 2-inch diameter, and a 1-inch diameter. We heat a reservoir of water to a temperature near boiling and leave the spheres submerged until they all come to that temperature at their cores. We remove the spheres and look at them with an infrared camera. Note that all the 3 spheres show up at the same high temperature as expected. Let's check your understanding with a prediction regarding what is going to happen in the demonstration. Which sphere do you expect will cool off first? Classroom students should follow normal procedures or instructor guidelines. Viewers not in a classroom should record your vote and explain your reasoning on a piece of paper. Please pause this video and answer the question. We will speed up the frame rate of our infrared camera and watch the sphere slowly cool by emitting infrared radiation. There is also some conduction due to the air. Note that the smallest sphere has cooled considerably while the 2 larger spheres are still quite warm. A little later, we can see that the 2-inch sphere is considerably cooler than the 4-inch sphere. The large sphere started with the most heat energy because of its volume. It also lost the most due to its large surface area, but it is still the warmest because the heat energy it possesses due to volume is greater than the loss from its surface area. The spheres, 4-inch, 2-inch, and 1-inch diameters, crudely represent the terrestrial bodies Earth, Mars, and the Moon, although Mercury works here too. Earth is still about 6,000 degrees Kelvin today in its interior, the same as the surface temperature of the Sun. This heat is working its way to the surface, where it is emitted as infrared radiation. Escaping heat can be seen in volcanoes and earthquakes due to plate tectonics, and in the surrounding magnetic field due to convection currents in the liquid outer core. There is still considerable heat energy in Earth's interior. The Moon, represented by the smallest sphere, is solid and cold all the way through. We see no evidence today of geologic activity nor a global magnetic field around the Moon. Mars is represented by the 2-inch sphere. Mars shows rather recent evidence of volcanic activity. It isn't clear if it can ever be volcanically active again.